Hello everyone, this is our session 5 on trigonometric functions. We had finished with the sine rule yesterday and different types in which you can present the sine rule. Okay, next we'll move on to the cosine rule. Okay, so let us begin with cosine rule now. We'll do the proof along with this cosine rule. Okay, so what is the cosine rule? It says a square is equal to b square plus c square minus 2bc cos A. Okay, b square is equal to a square plus c square minus 2ac cos B, and c square is equal to a square plus b square minus 2ab cos C. So that way it's simple to remember. The left hand side and the right hand side both have square terms, first thing. Secondly, we start with the first left hand side. If I say a square, then it will be equal to addition of the other two squares, b square plus c square, subtraction of 2 times the first two terms, b and c, okay, cos of the given left hand side, that is cos of capital A. Okay, again, b square will be addition of the next two sides, leaving b square, a square plus c square, minus 2 into single of each of the first two terms, ac, 2ac, cos of b, that is your left hand side again, and then c square is equal to a square plus b square minus 2ab cos c. Okay, so let us begin with the proof. Now, in the proof, there are three cases. So we'll prove only one statement. Similarly, you can prove the other three, or you can write similarly for the other three. Okay. So the statement that we are going to prove is to prove that a square is equal to b square plus c square minus 2bc cos of A. Okay, we have to prove this. Now the diagram for it. So the diagram will consist of your xy axis. Okay, we've considered point A as the origin. Okay, so the coordinates of A will be 0, 0. From A we've drawn the line AC, CB and AB. So ABC is your triangle with coordinates of A being 0, 0, coordinates of B C, 0, and coordinates of C will be B cos A and B sin A. How do we get those coordinates? A is this angle over here, okay, theta. So this is A. So we just have to drop a perpendicular from here. When you drop a perpendicular from here, cos A will be adjacent upon hypotenuse, that is AC upon B. So AC is the x coordinate for C. So AC will be B cos A, and similarly y coordinate will be B sin A. So we just drop this perpendicular here and find the value. Okay. So those are the coordinates of point C. Now how do we start the proof? So in the proof we have to mention that point A is the origin. So let's begin. Proof. Point A is origin. Okay. Therefore, A's coordinates will be 0, 0. B's coordinates then will be C, 0. Okay. And C's coordinates are B cos A and B sin A. Okay. Now, how will we prove A square? So our left hand side is A square. So let us start. A square is equal to BC square, correct? Now BC square by distance formula, the distance formula for BC the whole square, okay, which is equal to C minus B cos A the whole square plus 0 minus b sine a the whole square. Okay, which will be equal to c square minus 2bc cos a plus b square cos square a, formula of a plus b the whole square, plus b square sine square a. Okay, this is our formula. So if you can observe, this term will become b square common, cos square plus sine square is 1. So we'll get c square minus 2bc cos a, okay, plus b square. So our final product will be a square is equal to b square plus c square minus 2bc cos a. Okay, so what have we used? We have used the distance formula, okay, and solved the to prove that. So a square is addition of the other two squares, b square plus c square minus 2bc cos a. Okay, this is for a square. You can similarly use the same thing for b square and c square. Okay, so let us go to the next topic now. This was our cosine rule. Okay, cosine rule. After that, we're doing projection rule. Now, what is projection rule? Projection rule says that A is equal to B cos C plus C cos B. Okay, B is equal to A cos C plus C cos A, and C is equal to A cos B plus B cos A. Okay, this is what is the projection rule for sides and angles. So we have to prove this. So let us write the proof for any one of them. Yes, so we'll prove any one condition, any one statement, and then we can say similarly for the remaining two. Okay, so let us begin. We are going to prove that A is equal to B cos C plus C cos Okay, so this is B cos C plus C cos B. Okay, now how does the proof go about it? So we'll say consider all possible cases, okay, of or for angles B and C, that is their acute right angle or obtuse angle, and we'll prove any one situation. So one condition we'll take. So we'll say we've taken the condition, so we are going to prove that condition only, the first one. So what will our case 1 be? Let B and C both be acute angles. Okay, so draw AD, this is our construction, AD perpendicular to BC. Okay, also we are taking case 1 as B and C are acute angles. Okay, this is our first case. Then we'll say that now BD, okay, BD is projection of AB on BC. Okay, so AB is projected perpendicular. How much is that projection? BD. Okay, like point A and point B meet at point D. So BD is the projection of AB. Similarly, we can say that DC is the projection of projection of which side? It will be AC on BC. Okay, this is the projection. Now, how will we write this? So we say cos of B, okay, is equal to, now what is cos of B? This angle. Cos of B is adjacent side BD upon hypotenuse, that is C. So BD upon C. Therefore, C is equal, C cos B C cos B is equal to BD. We'll name this as 1. Okay. Then cos of C, okay, is equal to, now what will cos of C be? Adjacent side DC upon hypotenuse, that is B. So DC upon B. Therefore, DC is equal to B cos C. Okay, this we'll mark as 2. We now look at the figure. We can say BC is equal to, base BC is addition of BD plus DC, right? Which is, what is BD and DC? It is the two equations that we have found out. So that is C cos B, okay, plus B cos C, correct? And what is BC from the diagram? The entire BC length is opposite to angle A, so it is A. Okay. What I'll do is I'll just write this A here so that there's no confusion. Put this A here. So it stands for the entire BC length. Okay. Now we'll write A is equal to B cos C plus C cos B. Okay, this is our first statement, but for the first condition. What is our first condition? Case 1, that is B and C are acute angles. Now I'll say that my second condition, case 2, I have to prove it for case 2 also that this is true. What is that? Angle B is obtuse angle. Okay, obtuse angle. Now angle B is obtuse angle, so our diagram will change, right? So let me draw the diagram for the same. Okay, so the diagram will have angle B as an obtuse angle, okay, and I have drawn the projection and the perpendicular AD over here, okay. So again, the projection of AB will be BD only. So I'll just repeat the sentences over here. BD is projection of AB, correct? Because if you can observe, we've dropped a perpendicular from A and B. So ADB is 90 degrees. That means BD becomes projection of AB on BC. Okay, on BC. Similarly, for AC, we can write that. Now, where is the 90 angle formed? It is formed at DC. So we'll say DC is projection of AC on BC. Okay. Now we'll again form the cos angle. So now you have to observe that B angle over here that we'll take will be cos of 180 minus B, because B is this obtuse angle here. So the remaining acute angle will be given by 180 minus B. Okay. So we'll write cos of 180 minus B, okay, is equal to BD upon, what is the hypotenuse? C. Okay. Now what is cos of 180 minus B? It is minus cos B. Okay. Equal to BD upon C. We'll send C on the other side. So BD is equal to minus C cos B. Okay. This is the first equation. Similarly, we'll write cos of C. So cos of C is equal to, what is adjacent side now? 90 degree angle is at D, which is outside. So cos of C will be DC, okay, adjacent side DC upon B. Therefore, DC is equal to B cos C. Okay, DC is equal to B cos C. Now what is our next step? We write BD, sorry, BC. The base again we'll take the same way like we took in the previous one, BC, that is A. So we'll say BC is equal to, now look at the diagram. The diagram says BC is DC minus DB. Subtraction will be there, right? So DC minus DB. Now what is DC from our previous step? It is B cos C. We'll put 2 here and we B cos C minus BD is minus C cos B. Okay, and here you can write from 1 and 2. Okay, so we'll get B cos C plus C cos B. And what is your left hand side? It is side A. So A is equal to B cos C plus C cos B. Okay, so we prove two conditions when, let us see, look at case 1. It says B and C are acute angles. Okay, and then case 2, we have proved angle B is obtuse angle. What will be case 3 then? Case 3 will be angle B is right angled. Now if angle B is only right angled, do we require AD or will it merge with AD? Yes, so the triangle itself will become a right angled triangle. Okay, so let us draw a right angled triangle here. Yeah, and the naming will be, this is A, this is B, and this is C. This is A, B, and C, 90 degrees, right? Now, what will be projection of AB on BC? It will be AB only, right? And projection of AC on BC, it will be BC only. So you don't have to write that. Okay, how we will prove this then? What do we have to prove? A is equal to B cos C plus C cos B. So we'll just use a different method for proving this. Okay, C cos B. Okay, so we'll take the right hand side. Okay, and we'll say B cos C plus C cos B. Now what is B angle? It is 90 degrees. So let us substitute 90 degrees in place of capital B. So C cos 90. Okay. What is cos 90? It is 0. The second term becomes 0. We are left with B cos C. Now what is cos C over here? This cos C. So cos C is adjacent A upon hypotenuse. So B cos C will be equal to A. So this is equal to A equal to the left hand side, and therefore we have proved the condition for right angle as well. Therefore we can say A is equal to B cos C plus C cos B. Okay, so we have proved the condition for all the three cases. The first one is B and C are acute angles. Second one is B is an obtuse angle, and the last one is B is a right angle. This is for any one statement. You can then write similarly for the other statements. So let us go through the projection rule once more. A is equal to B cos C plus C cos B. Okay, B is equal to A cos C plus C cos A. The left hand side is not put inside the right hand side. You will observe that it is different and it is alternate. That is A then cos C, C then cos A. Okay, and then C is equal to A cos B plus B cos A. Okay, so this is your projection rule. Finished with the sine rule, the cosine rule, and the projection rule. Now there are applications of these rules. So what are these applications? Let us begin with that. The first application is the half angle formulae. So with the help of these rules, we can find out the half angle formulas for sine and cos. So half angle formula for first let's start with sine. So sine a by 2 is equal to under root of fraction root. So under root of s minus b, s minus c upon root of bc. Okay, and cos a by 2, half angle of a, cos a by 2 is equal to under root of s minus a, s into s minus a upon bc. So if you use this, then we can write the half angle formula for tan also. That will be tan of a by 2 is equal to, we'll divide the 2. So what do we get? S minus b, s minus c. Okay, that's your numerator, and your denominator will be s into s minus a, right? So that will be your denominator, right? Tan a by 2. Now how do we prove this? So similarly, see, from sine a, cos a, tan a, we've got out sine a by 2, cos a by 2, tan a by 2. Similar ratios can be written for sine b by 2, cos b by 2, and tan b by 2. And the third angle, that is c by 2, sine cos c by 2, and tan c by 2. Okay, so we can write it for the other angles as well. Now we'll prove the first one, that is sine of a by 2 is equal to under root of s minus b, s minus c divided by bc. Let us prove this. So for the proof, we are going to use the rules that we have studied: sine rule, cosine rule, and projection rule. So let us begin with one identity that we know: 1 minus cos a is equal to 2 sine square a by 2. Okay. Now we'll use the cosine rule over here. Okay. So what is the cosine rule? If I want cos a, so I'll write a square is equal to b square plus c square minus 2bc cos a, right? So what I'll do is, I just want cos a now. So we'll put all the terms on the left. So a square minus b square minus c square, right, upon 2bc is equal to cos a with the minus sign here. So what we can do is, we can shift the minus sign to the numerator. So that will be c square plus b square minus a square upon 2bc, right? So what we'll get the next step as, when we substitute the cosine rule, we get 1 minus bracket b square plus c square minus a square upon 2bc is equal to 2 sine square a by 2, right? Now next step, taking LCM, so we'll have 2bc minus b square plus c square minus a square, okay, upon 2bc is equal to 2 sine square a by 2. Okay, now we'll put this 2. So we'll have 2bc minus b square minus c square plus a square, right, upon 2bc is equal to 2 sine square a by 2. Okay, right? Now what we'll do is, we'll write we'll combine these three terms together. So how do we do that? We'll write a square, okay, minus b square minus c square, one second, minus 2bc upon 2bc is equal to 2 sine square A by 2. Okay. Now what we'll do is we'll expand this bracket, not expand, rather we'll put it in this form. Is this correct? B square plus C square minus 2BC makes an identity, whole square identity. So we write it as B minus C the whole square upon 2BC equal to 2 sine square A by 2. Okay. Then we can use the second identity, that is A square minus B square is A minus B, A plus B. So here it will be A minus B minus C. Okay, this is your first bracket. Second bracket, A plus B minus C, right, upon 2BC is equal to 2 sine square A by 2. Okay, now what will be the next step? B plus C. Okay, as in the first bracket we have A minus B plus C. So A plus C is already there. I've introduced plus B and there is a minus B minus B. Okay, that means I have introduced this new term, so I have also introduced minus B with it, and there is already a minus B present in it. Okay, and in the same second bracket also I'm going to write A plus B plus C. Okay, so now in the second bracket A plus B is there and there is a minus C. That means I have introduced a plus C. So I will also introduce a minus C to cancel it out, and the minus C that is already present in it, and then the 2BC. Okay, now this will be equal to so we'll have A plus B plus C minus 2B, right, and A plus B plus C minus 2C, okay, upon 2BC, right. Now what is A plus B plus C? It is 2 times the semi-perimeter, okay, minus 2B as it is, and this is again 2 times the semi-perimeter minus 2C as it is, divided by 2BC, right. We'll take 2 common, okay, and we'll get 2 outside, S minus B, 2 bracket S minus C, 2BC, and what was the right hand side? 2 sine square A by 2. Sine square A by 2. Okay, so 1, 2 cancels out here, the other one cancels out here. Taking square roots on both sides, you will have S minus C and S minus B upon BC equal to sine A by 2. In similar way, you can prove cos A by 2. I'll just tell you the identity. The identity will, how we started this sum, we started with 1 minus cos A. Okay, 1 minus cos A, right? So now the second cos term, cos A by 2, how will you prove that? We'll use 1 plus cos A is 2 cos square A by 2. Okay, and then we'll start as we did it in the previous one. That is, we'll substitute cos A again and get the formula for cos A by 2, right? So that will give us the half angle formulas. After the half angle formulas, what is the other application of these sine rules, cosine rules? So we have one more called as the Heron's formula. We've heard of it before while finding area of triangle. So what is the Heron's formula? Area triangle ABC is equal to under root of S minus A, S minus B, and S minus C, okay, where what is S? Where S is equal to A plus B plus C upon 2, semi-perimeter of a triangle. What is A, B, and C? Value of the sides of the triangle. Okay, this is your semi-perimeter. Now, using the sine rule, cosine rule also, you can find out this formula. So I'll just show you the proof of this. Okay, how will you prove this? So area triangle ABC is equal to half AB sine C. We have done this in the sine rule when we wanted to prove sine rule. We've used this formula only. Area triangle ABC is half AB sine C. Okay, so how will we write this now? Half AB, okay, and sine C can be written as 2 sine C by 2 cos C by 2. Half angle formula, you can say expansion of sine C can be written as 2 sine C by 2 cos C by 2. So this gets cancelled. Now we have AB sine C by 2 and cos C by 2. What formula will we use here? We'll use the half angle formulas now. So area triangle ABC is equal to half AB as it is. Okay, in the bracket, what will be sine C by 2? From the formulas that we just learned, okay, we just did this, right? Sine A by 2 is this. So sine C by 2 will be what? See, remember, when you write A by 2, in the answer there is no A. There are the other two values, S minus B and S minus C upon BC, right? So what will we do for C then? Sine C by 2 will be under root of S minus A, S minus B, right, upon AB, correct? And what will be cos? Cos has the same angle, so with the root sign again, right? S minus C divided by root of AB. Divided by root of AB. Okay, we put the square bracket. Now what will happen? We'll have AB cancelling out each other because there are two roots over here and this AB cancels out, right? So root of S minus A, S minus B, S minus C will be as it is. Okay, the 2 we have already cancelled. By mistake, I have put it over here. Sorry for this. Okay, in the previous step, the 2 was already cancelled because we've done 2 sine C by 2 cos C by 2. So the 2 gets cancelled. So we are left with under root of S minus A, S minus B, and S minus C. So what are the two formulas we use to prove this Heron's formula? First one, AB sine C. We have used, you can say we have used the sine rule also over here. So there is sine rule from here. Then the next step, we've used half angle of sine C, that is 2 sine C by 2 cos C by 2. And then the half angle formulas in terms of A and B. Okay, so this is how you prove the Heron's formula. The last application is the Napier's analogy. Okay, now what is the Napier's analogy? Let us see. In triangle ABC, tan of B minus C upon 2 is equal to B minus C upon B plus C cot of A upon 2. Okay, this is Napier's analogy, can be written for the remaining angles also. So tan of C minus A upon 2 is equal to C minus A upon C plus A cot of C, so B by 2. Okay, and tan of A minus B upon 2 is equal to A minus B upon A plus B, right? Cot of, which angle is not there, that one we put over here, cot of C by 2. Okay, so there is a kind of analogy in all the formulas that we have written by now. Some of them, if the left hand side term is A, then the right hand side does not have it or has it in the end. Like for cosine rule, how do we write it? A square is equal to B square plus C square minus 2AB, minus 2BC cos of A, right? So if you find a method of remembering them, it will be easier Okay, like over here in the in the Napier's analogy, tan of b minus c upon 2 can be written as it is b minus c angle, so the ratio is also the same, b minus c, b plus c, and cot of the angle, which is not mentioned at all, half angle, that too, the cot of a by 2. Even left hand side, you observe they are half angles, b minus c divided by 2, c minus a divided by 2. So they are half angles basically. You can check the proof in the textbook. It's simple. We'll go to the exercise in the next session, which is based on all these theories that we have just studied, all the formulas. So in the next session, we'll first go through all the formulas together, and then we will go on to the exercise. If you have any doubts in the proofs that we have done, you can write to me. I'll explain them again. Okay. Thank you very much.